The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly straight down. Some of the fundamental physical principles include Newton's second law. Newton's second law relates the net interaction between the system and its surroundings, the observed motion of the system. The net force is the vector sum of all forces acting on the system. In our experiment, the net force will not be equal to 0 since the falling object has a non-constant velocity. So what exactly are these forces that are acting upon the falling object? With the falling object, there are two forces acting on it, the force of gravity and the drag force. Gravity is a constant force that always points down towards the ground. Near the surface of the Earth, gravity, which is represented by g, is 9.8 meters per second squared and is the magnitude of acceleration. The force of gravity, also known as the weight force, is calculated by multiplying the gravitational constant g and the object's mass. Drag force, also known as the air resistance force, is the resistance force that is opposite to the direction in motion. In the example of the experiment, the drag force is acting against the downward motion of the falling object. This is represented by the equation F drag is equal to negative b times the magnitude of v squared times v hat. B represents the proportionality constant that depends on airflow and the object's properties like its shape and size. The magnitude of v is just the speed of the object, and v hat is the velocity direction. Knowing the force of gravity and the drag force, the two values can be added to find the net force. In the results, there will be three different models plotted on the same graph, one experimental and the other two computational. With the experimental model, I used Tracker to analyze the recorded video of the folded piece of paper falling to extract the paper's position and corresponding time, allowing me to plot the observed position versus time. With the computational models, I used GlowScript to construct both of them, one that includes only the effect of gravity and the other that includes both the effect of gravity and drag. In the results, the computational model that accounts for both drag and gravity is more accurate to what's observed in the experimental model than the computational model that only accounts for the force of gravity. As you can see in the video, the system is the folded piece of paper and the surroundings is everything else surrounding the system, which includes the earth and the air. These surroundings interact with the system through gravity and air resistance. In our experimental model, I used the video of the paper and tracker to plot the object's position as a function of time. The paper moves top to down going in the negative y direction, resulting in a downward sloping graph of position versus time. To make the computational model, I first set the initial conditions in the GlowScript. I changed the object's mass to be 0.0045 kilograms, which is the mass of my paper. Using my data from tracker, I set the initial position of my paper at t equals 0 seconds to be negative 4.553 times 10 to the negative 3 meters. The initial velocity is left to be at 0 meters per second because the object is initially at rest. As for delta t, the time step in the code is 1 over the frame rate I recorded at 30 frames per second, which matches the time step seen in tracker. And lastly, g is set to be 9.8 as the gravitational constant on Earth, and b is equal to 0 since this is the computational model where we don't account for drag force. With the initial conditions established, I'm able to implement the formula for the weight force, which in this case is the net force since this is the computational model that only accounts for the force of gravity. The weight force is equal to negative m times g times j hat. J hat is just a direction vector that is already set in the initial conditions. The reason why the weight force is negated is because the object is moving towards the Earth, which we established as going in the negative y direction. You can also see that I've included Newton's second law in the position update formula so we can predict the object's velocity and position. Here's the graph of both the observed position and predicted position as a function of time, with the predicted values only accounting for the force of gravity. Looking at the graph, the computational model initially shares the same points as the experimental model, but after some time, the computational model differs from what's observed and has a steeper slope. Seeing how the computational model doesn't really follow the observed data, there must be another force acting upon the object that isn't just gravity. The other force acting upon the falling piece of paper is the drag force. So let's make a second computational model that accounts for both drag force and the force of gravity. The initial conditions mostly remain the same, but for the constant b, I set mine to be 0.008392. To find the b constant, I first included the F drag formula in the while loop mentioned in the introduction. I also changed F net so it equals to the weight force plus the drag force since this is the model that accounts for both forces. With those equations included in the code, I found b by setting it equal to different values and chose the value that gave me the computational model that best matched the data points in the experimental model. Here are the results where I've included all three models on one graph. As you can see, the predicted position of the computational model that accounts for both gravity and drag is the one that closely matches the observed position in our experimental model. The gray points almost directly overlap with the blue points because that's the computational model that most accurately reflects the motion of the falling object in the real world, where F net is the sum of the drag force and the force of gravity. With the orange points, the computational model only includes the force of gravity as the net force, making it inaccurate to what is actually observed. Moving on to some discussion questions. Which models, if any, predicted terminal velocity? The terminal velocity happens when the drag force pointing up has exactly balanced the force of gravity pointing down. This means that the net force will be equal to 0 and the object is at constant velocity. Looking at both graphs of predicted velocity, the graph on the right that accounts for both gravity and drag predicts the terminal velocity as the downward slope starts to plateau into a straight line, indicating a constant velocity. This differs from the graph on the left, which shows a downward sloping line indicating a constantly decreasing velocity. What if the object was initially thrown downward? The terminal velocity would still be reached, however the magnitudes of the terminal velocities would differ. This can be checked by setting an initial velocity in GlowScript. On the left is the predicted velocity versus time with an initial velocity of 0 meters per second. You can see the line starts to plateau when the velocity is equal to negative 2.25 meters per second. On the right is predicted velocity versus time with an initial velocity of negative 2 meters per second. You can see the line starts to plateau at a greater magnitude where velocity is equal to negative 2.30 meters per second. Even though in both cases the terminal velocities reached, magnitudes of these terminal velocities differ. Some possible sources of error include human error and issues of the object's surroundings. When using tracker to track the motion of the falling paper, it was was difficult to mark a consistent point of mass as the paper flipped when falling towards the ground. This could have made the observed position inaccurate to what was actually happening. There could have also been issues with the paper's surroundings. Wind or other factors could have made it so that the forces acting on the object wasn't just the force of gravity and the drag force. These errors could have accounted for the slight difference between the observed data and the predicted data that accounted for gravity and drag seen in the middle of the graph. When dealing with a falling object, or really any object in motion, it's important to consider both gravity and drag force to give an accurate model of what is actually occurring in the real world. Without accounting for drag force, your model of a falling object will not reflect accurately to what's actually happening.